Now that we have laid out the balance equations for a closed process, let's look at different types of closed processes. But first, let me write the equation that we developed for describing a closed process. If you recall, the delta E equals Q minus W external. And most of the time, KE and PE are negligible. And this is what we get for energy equation. Similarly, the entropy equation is Q divided by TB Sgen. So let's keep these equations in mind and let's visit some animations to explore. Now the first one, this is a little bit abstract, but look at we want to figure out the meaning of the TS and PV diagram. First of all, so here we have a system that is going through a process from a B state to a F state. And of course, we know that the work transfer is given by the boundary work is given by the area under the PV diagram. Strictly speaking, it is true only when the system is internally reversible. So this is a handy formula to remember. The area under the PV diagram is the boundary work. Of course, if it is instead of V specific volume, then it will be boundary work per unit mass of. But look what we get if we take a look at the entropy equation. If you recall, the entropy equation for is something like ds over q over tb plus sgen. So if we take the internal system and it's reversible, internally reversible, this goes to 0. So in other words, if we add a very small amount of heat, then the change in entropy will be kind of dq over T, because internally the temperature, boundary temperature, and the system temperature are the same. So therefore, as you can see, if we integrate this equation, we get integral TdS become the proportional to, not proportional, exactly equal to the internally reversible work, reversible heat. So if it is entropy per unit mass, we are dividing by mass. Therefore, we can see that the area underneath is proportional to the heat transfer. So you draw a TS diagram for a closed process and a PV diagram. One plot will tell you, quantify, give you a visual picture of heat transfer. Another diagram will give you a visual picture of boundary work transfer. So these concepts become very important when we study, let's say, IC engines. In ME 351, we'll be doing that. So this will become useful later on than right now. So for the time being, let's go and explore several other systems, several other processes. We already done some constant volume. Remember the heating process, we even solved a problem. So these are straightforward. The mass, energy, and entropy equation you have already encountered. This is a heating of a solid block. This is a solid cooling. So I would suggest you go over this animation. So this is a constant volume heating. And we'll do some problems like that, but you can see that when the gas is being heated, the mass, of course, remains constant. The energy equation is the same old. There is no work transfer because there is no change in volume. Entropy equation similarly will give you entropy generation, and the energy equation will give you the heat transfer. So constant volume processes are relatively easy to solve. Let me go to a constant pressure process. These are all examples of constant volume, see V constant, so you can browse through them. This is an example of a constant pressure heating involving an ideal gas. Again, our focus should be what will be our mass, energy, and entropy equation. First of all, look at the system, the system being the gas inside the piston cylinder device or the fluid. As I heat, there is a heat transfer. The fluid expands, so it probably is a gas or vapor. As it expands, it pushes out the piston, lifting the weight and lifting the atmosphere on top of it. Don't forget the outside atmosphere. So there is a lot of boundary work that is crossing the piston boundary. So there is heat transfer, pouring energy in, and boundary work taking energy out. And of course, the temperature of the system changes. So if you look at the energy equation, delta E, which is equals delta U, if KE and PE are negligible, tells us that Q minus W external, which is, in this case, energy is coming out by work. So Q in minus W out is this. So this becomes our energy equation. Entropy equation is again straightforward. The work doesn't involve entropy, so it remains the same. So we can go on, and there are more and more processes that are discussed here. So let's go over a constant entropy process. Let me see if I find one. So in this case, okay, let me see if I find a little bit better picture. So we want to go for an isentropic process. Okay, so the isentropic process is a very important process. So let me just go to the PowerPoint and explain when do you encounter an isentropic process. It could be an expansion or compression of a gas. So suppose this gas is compressed and it is pushing the piston out, and let's say there is a force on it which is adjustable. But also we say the piston cylinder device is insulated. So immediately we know Q goes to 0. And now suppose we say as the gas expands, there is no friction inside. So we are putting two conditions. One is the process is adiabatic, no heat transfer, and no internal friction, which means you know what quantifies friction, entropy generation. So if these two conditions are satisfied, as you can see, then delta S becomes 0, therefore S2 equals S1. In other words, the system, in this case, the gas will expand without a change in entropy. So that is very possible. Similarly, if you compress a gas, the same thing happens. Entropy can remain constant as long as it's adiabatic, number one condition, and number two is what? There is no internal friction, which is a very good assumption, because if you think about it, a gas, when it is compressed, its pressure increases everywhere simultaneously. Its temperature increases everywhere simultaneously. So there is not too much internal differences to be destroyed. There is not too much internal friction. But how can you make sure that Q equals 0? One is, of course, that if you insulate the system. Another is if you compress something very quickly. If you take a gas and very quickly compress, then there is not enough time for heat transfer. So therefore, that's another case. So in a car engine, when air is taken into a piston cylinder device and the piston rams the air to a small volume, we'll see isentropic processes occurs. So let's go and solve a number of problems with different kind of processes, then these ideas will solidify.